So today we're going to do a dual motor torque bias. So the idea is both these motors will work together to drive the load. Um, Sometimes the load is a gear, which is then attached to the load. So two motors with gears on them driving another gear, like a gear and a sprocket. But you get there's a little play in the gears sometimes, and you want to bias them a little bit, a little forward or a little reverse, depending on which way you're going. And so what I've done here is I've turned on the torque bias, and I've got the A axes. I got a BP2, a 2-axis drive, which I'm just doing velocity mode. We could do position mode and cross coupling and all that stuff, but we're trying to demonstrate the torque bias. So velocity mode without a lot of integral is good, and that allows the torque to be applied, a positive torque for A and a negative torque for B, so they oppose each other. So that it's always one is biased to keep the deadband out of the gear. Anyway, so I can move them together, and this is not the cleanest mechanical system here, but forward and reverse, they're both doing work on the same load, and the tape is starting to come off, which is okay, just as planned. So you can see they're commanded with zero velocity, but there is some motion on it. It's just a torque. So I can easily, I got like 0.05 amps here, so I can put them together again, but they tend to try to split apart, which will get rid of the deadband in the gear, that if there was a gear between them. Let me show you how I've got it configured. So the first axis is the A axis, and it's configured in a velocity mode software program so I can jog it. The B axis is configured as a slave to the A axis, velocity in this case. I mean, we could do position slave or current slave. It's two velocities getting the same commands. One is forward, one's reverse. It's just they're just phased differently to show that effect of turning together. You know, one's clockwise, one counterclockwise. They face each other and they go the same way. The only thing different I've done here is I've applied a bias of a current offset, like a gravity in the negative direction on one, and then the positive direction, like a bias on the other. And so we can see that when we're jogging the motors now, they go together, but there's a slight bias or lag in the slave going this way, and then when you go negative, there's a slight bias or lag in the master because of the offset current. So they're actually, they look like they're turning at different rates, but that's just the error based on the acceleration or the current or the torque bias that's applied, and that gets rid of the deadband in the gear. So let's look at a system diagram here. So the load is attached to a gear in the middle, and there's two motors that are working. They're spinning in opposite directions to both work on controlling the velocity of the load. I suppose we could do this in the position loop too. I just turned the integrators down. So just gonna double check that I did that. Yeah, no integral, a little bit of steady state error allows the bias to show through. Maybe we should use some integral, so that's okay. It's just that will counter affect the bias effect. Anyways, these two motors, typically when we do like an antenna where two motors are working together to move the one big antenna, we will command the velocity the same to both. And typically a master could decide, hey, I'd like to move this one forward a little bit with velocity, or that one forward a little bit with velocity. So we can measure the other axis velocity back to the master and then recalculate and command an offset. This is how to use a master to do this, keeping them together by measuring each other's velocity. So if one sped up, you could slow one down, or if the other sped up, then you can slow the one down. But what I've done here is I've just configured one as a master and then command the velocity, and the other one's just a slave, so that takes the can out of having any responsibility. But now we have to come up with getting rid of the deadband in here, so we add a current offset, and so this parameter AE is the current loop offset in units of 0.01 amps or 10 milliamp quantums. So you can do small amounts of current. The application that I worked on maybe had plus 1 amp for one and minus 1 amp for another, so a more substantial torque bias. So each axis has its own parameter. The A axis, like node 1 or something, has it, and then the B axis, maybe that's node 2 on CAN, or the second slot of an EtherCAT. So you can address it. Each node's individual plus or minus value for offset. And so available over CAN is a standard CAN object or over the serial port. And here I've just used CME to do that. So maybe we can't see the effect very well. So let's go. Yeah, there we go. So we see one going much faster than the other. Although, you know, they're working together. That's just the torque bias slowing that one down. And then going the other way. So when there's an error in the command and an actual velocity, of course it'll generate current, throw some integral in there, and the error will be reduced. But, so for demonstration purposes, it's overly exaggerated. So yeah, typically you would use some integral in here. So I tune the loops. I'm going to set the A axis with integral of 300, and I'm going to do the same for the B axis, 300. So just velocity loop, some integral, reduce the error over time. And now there's not so much torque. Oh, sorry, jogging the wrong thing here. Don't jog the B axis yet. And so let's make the B axis, the mode of operation for the A is this. We're in current program mode. Sorry, I hit the checkbox. You can disable, you can re-enable, and there's the bias current, and that's it. So now jog the A axis, which is the velocity program mode, and make sure the B axis is the slave. Don't jog the B axis. So jogging the master, nice and slow. And you can see how the integrator is keeping them, keeping their velocities. And so if there's a deadband in the gear, it will have been eliminated. And then the bias applies in the other direction. If you keep this up, you may see a slow variation in the velocity. They're starting to catch up a little bit there. Anyways, that's first experiment with torque biasing, working in a real application. That seems to be what did the job for it. So thanks for watching.